Hello friends, I am back and today we are going to learn about the modern periodic table. In 1913, Henry Moseley showed that atomic number is a more fundamental property than atomic mass, and therefore he gave the modern periodic law. So modern periodic law stated that the periodic properties of elements are a periodic function of their atomic numbers and not their atomic masses. Now the question was the modern periodic law able to overcome all the limitations of the Mendeleev's periodic table? Let's take a look. So let's look at each of the limitations one after another. First, position of isotope is clear now. How? Let's take examples of isotopes. Let's talk about C12, C13 and C14, which are the three isotopes of carbon. Now, where are these placed in the modern periodic table? Well, since all of these isotopes, they have the same atomic number, which is 6, therefore they have just one position on the periodic table. So different isotopes do not get different positions because now the elements are placed based on their atomic number. So isotopes position was clear. Next, position of cobalt and nickel. So in the Mendeleev's periodic table, we saw that cobalt had lesser atomic mass, but still it was after nickel. So there was a confusion. But now it was all sorted because cobalt has atomic number 27, nickel has 28, and they are very rightly placed. Third limitation, position of hydrogen. Now that was also sorted because if we look at hydrogen, it has an atomic number of 1. Therefore, the electronic configuration is also 1. It has 1 valence electron, so it is in group 1 and period 1. So this is also sorted. And finally, the fourth limitation, is it possible to have an element between two elements? Okay, now this was perfectly sorted. So if you look at it, the first element is hydrogen, which has atomic number 1. Second is helium, which has atomic number 2. Third is lithium, which has atomic number 3. Now, is it possible to have elements in between them? Maybe with atomic numbers 1.2, 1.5, 1.7 and so on. No, that's because what is atomic number? Atomic number basically tells us the number of electrons, right? So, atomic number is always a natural number. You cannot have a decimal number as atomic number. Right? So therefore, can you have a natural number between 1 and 2 or between 2 and 3? No. Therefore, you cannot have an element with atomic number somewhere between 1 and 2. Therefore, there are no chances that in future a new element might come up which will have atomic number in between two of these elements. So that possibility was ruled out. So we see that with this modern periodic table where the elements were arranged based on their atomic number, most of the shortcomings that we had so far were all sorted. So therefore, based on all of these observations came up the modern periodic law, which stated that properties of elements are a periodic function of their atomic numbers and not atomic masses. So basically, it showed that atomic number is a more fundamental property. Now, what was the basis for this law? Now, when these elements are arranged according to their increasing atomic numbers, we see that elements having same number of valence electrons occurs at regular intervals. And we will see very soon that the number of valence electrons, they play a critical role in deciding the properties of elements. Therefore, we see a periodicity in the properties of elements as well. The modern periodic table has 18 vertical columns called groups and 7 horizontal rows called periods. Let us now talk about periods and groups. So we will start with periods. What is a period? Any horizontal row of element in a periodic table is called period. For example, if we talk about the first period, it consists of 2 elements, hydrogen and helium. If I talk about the second period, it has 8 elements, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon, and so on. Now, the speciality or some specific features of periods are they have consecutive atomic numbers because the elements are placed in this fashion. So, one after another. So, in one period, all the elements will have consecutive atomic numbers. Number of elements in a period is fixed by maximum number of electrons which can be accommodated in various shells of atom. Now this is an interesting fact, and it is also very important to understand this concept. Now if you look at it, you will see that in every period you have a fixed number of elements. For example, if you talk about the first period, you have 2 elements, hydrogen and helium. If you talk about the second period, you have 8 elements, lithium to neon. Third period, you again have 8 elements. Fourth period, you have 18 elements. Fifth period, you again have 18 elements. So basically what I'm trying to say is every period has a fixed number of elements. Now the question is, from where are we getting these fixed numbers? As in, from where did we get these numbers 2, 8, 18 and so on? Now, let us try to understand this entire logic. The number of elements in a period is fixed by the maximum number of electrons which can be accommodated in various shells of atom. We will quickly go back to the structure of an atom. So in an atom, you have the nucleus in this fashion, and then you have orbits around the nucleus in which the electrons revolve around the atom's nucleus, right? So let's talk about electron shells and let's see how do we get these numbers. Now, each shell has a fixed number of electrons. Now, for example, this is the nucleus. Now, you will have shells like K, L, M, N and so on. So that is how we name the shells. Now each of these shells has fixed number of electrons. For example, the K shell can only have a fixed number of electrons. L shell can only have a fixed number of electrons. And how do we know how many electrons can be there in each shell? So that is given by a formula 2n square. So this formula decides how many electrons will be there in which shell. So the value of n will keep increasing from 1, 2, 3, 4 and so on. So if we are talking about the K shell, the value of n will be 1. So the total number of electrons in K shell will be 2 into 1 square, that is 2 electrons. If we talk about the L shell, value of n will be 2. So 2n square will be 8. So in the L shell, we can have 8 electrons. If we talk about the M shell, value of n will be 3. So this will be 18. So M shell can have at the max 18 electrons. So in this fashion, we decide how many electrons can be there in each of these shells. Now, each of these shells consists of one or more subshells. So when we talk about the shell, these shells are made up of one or more subshells. And each of these subshell consists of one or more atomic orbitals. Now I am going a little deep so that you are able to understand from where are we getting these numbers. I do not want you to merely memorize the numbers. That is why I am going a little bit deep. But when you go to your 11th and 12th standard, you will anyways learn about all of these in more detail. Okay, so understand it in this way. So every shell, for example, if I talk about the K shell, so K shell has one subshell and that one subshell is 1s. If I talk about the L shell, so the L shell has two subshells, 2s and 2p. If I talk about the M shell, it has three subshells, that is 3s, 3p and 3d. Now what are these s, p, d and so on? So these s, p, d, they are the atomic orbitals. That is what I was talking about just now, right? So now you understand that these K, L, M, they are the shells. They are made up of subshells and the subshells are made up of atomic orbitals. So now to put all of these together, it looks somewhat like this. So you have these shells like K, L, M and so on. Now each of these shells has orbitals, they have subshells like 1s, 2s, 2p, 3s, 3p, 3d and so on. And each of these subshells, they have some fixed number of electrons. So therefore K shell can have maximum 2 electrons. L shell can have maximum 8 electrons. So M shell can have a total of 18 electrons and so on. Correct? So in this fashion, we decide that how many electrons can be there in each of the shells. And based on that only, we decide how many elements can be there in each of these periods. So you see, you are getting these numbers, right? 2, 8, 18, 32, and so on. Net, we see that the first period has 2 elements. So it is called a very short period. Second and third period, they have 8 elements. They are called short periods. Fourth and fifth period have 18 elements. They are long periods. And sixth one has more than 18 elements, and that is called very long period. It's time to learn about groups. So groups are the vertical columns in a periodic table. So the columns that you see, the vertical ones, they are groups. Now, elements in a group do not have consecutive atomic numbers. Now, that's very obvious because the elements are placed in the order of increasing atomic numbers. So, it is not possible that the elements lying below one another, they will have consecutive atomic numbers. All elements in a group have same number of valence electrons. That is true. Now, let us quickly consider this group and let us write their electronic configuration. So for hydrogen it is 1, for lithium it is 2, 1, for sodium it is 2, 8, 1, for potassium it is 2, 8, 8, 1. So you see that the number of outermost electrons, that is the valence electron, is 1 for all of these. In fact, we also see that all elements in a group have similar electronic configuration. So you see they have a similar pattern of electronic configuration. And since they have similar configuration, similar number of valence electrons, therefore they have similar physical and chemical properties as well. Number of shells increases as we go down the group. Now that's interesting. Let us suppose if we talk about hydrogen. So it has just 1 electron in the first shell. If we talk about lithium, so it has 2 electrons in the first shell and 1 in the next one. If you talk about sodium, it has 2 in the first, 8 in the second, and then 1 in the third. If you talk about potassium, it has 2 in the one, 8 in the second, 8 in the third, and 1 in the fourth. So you see, as we go down, the number of shells are increasing and therefore the atomic size also increases. Now, a most important question is, what decides the period or group of an element? So how do we know out of these so many elements? Now, if you know the electronic configuration, you will be able to decide the period and group of an element. Let us talk about finding the period first, okay, and then we will talk about how to find the group. Now, so far we learned that we talk about the concept of shells like K, L, M, N, and so on. Each of these shells consists of one or more subshells like this: 1s, 2s, 2p, 3s, 3p, 3d, and so on. And then there are fixed number of electrons which can be accommodated in each of these subshells, right? Now let us take an example. Let's talk about beryllium. So beryllium has an atomic number 4, right? So if we have to write its configuration in terms of shell, we will write it as 2, 2. 2 in K shell and 2 in L shell. 2 electrons in K and L shell respectively. If we have to write it in terms of subshells, it will be 1s2, 2s2. Now, the value of N of the valence shell decides the period of an element. Which is the valence shell? That is the outermost shell here, 2s. So in 2s, the value of N is 2. 2n is in the sense ns, np. So here 2 is the period of beryllium. So beryllium belongs to the second period. Perfect. Let us take one more example. Let us say, let's talk about, so we'll take one more example to understand this. And let's take scandium. So if we talk about scandium, which has atomic number 21, so it will be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. So this is the electronic configuration of scandium. Now I am not asking you to write this configuration because this is something which you will learn in your higher class in 11th and 12th. All that I am trying to show you is how we arrange these elements. So if you look at this one, which is the outermost shell, valence shell 4s. So 4 decides the period. So if you say scandium, it belongs to the 4th period. So this is how we decide the period. Another important thing is the number of valence electrons decides which will be the first and which will be the last element in a period. For example, all the elements, the first element of any period will have one valence electron. So even if you want, you can try this out. So let's say if you talk about hydrogen, electronic configuration is 1. You talk about lithium, electronic configuration will be 2-1. You talk about sodium, it will be 2-8-1. You talk about potassium, it will be 2-8-8-1. So in all of the first element of any period, we will have a valence electron 1. But as you go to the last element of the period, what do you see? It changes. So gradually, as you move from left to right in a period, the number of valence electron keeps increasing by 1 consecutively. And that's how by the time you reach the end of the period, the last element in the period, you have completely filled last shell. So in this fashion, we decide the period number of any element. What about group? Now, when it comes to group, there are a few rules, you can say. So basically, the number of valence electrons give us the period. But that is not true for all the cases. Now, in this periodic table, we have different categories of elements like S block element, P block element, and D block element. Now, what do we mean by S block, P block, and D block elements? Now, if the S orbital receives the last electron, it is called S block element. If the p orbital receives the last electron, it is called p block element. If the d orbital receives the last electron, it is called d block element. Let us take one example of each of these cases. First, we will take an example of s block element. So let us take the example of beryllium. So electronic configuration of beryllium is 1s2, 2s2. So the last electron enters into the s block. Therefore, it is S block element. And here, group number is equal to the number of valence electrons. How many valence electrons are there? 2. Therefore, this 2 is the group number. So, if you look at the periodic table, beryllium is in group 2. Now, let us take an example of a P block element. Let us talk about aluminium. So if you look at the configuration of aluminium, it will be 1s2, 2s2, 2p6, 3s2, 3p1. So this is how the electronic configuration looks like. So in this case, we have one valence electron. So do we have just one valence electron in this case? Not really, because both of these are 3. So these are basically the subshells. That means we have total 3 valence electrons, because when you write its configuration at the shell level, it will be like 2, 8, 3. So we have 3 valence electrons. So you see this 3s and 3p, both of them are part of the M shell. So the outermost shell is M, but the outermost subshell is P. Correct? So here total number of valence electrons is 3, but as per rule, group number will be equal to 10 plus number of valence electrons. So 10 plus number of valence electrons, that is 13. So 13 will be the group number. So you see aluminium, it belongs to group 13. Let us now talk about a D block element. Let's talk about manganese. So manganese has 25 atomic numbers. So if we write its configuration, it will be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d5. So which is the valence subshell? This is 3d5, right? So how many total number of valence electrons do we have? So in the D shell, we have 5 valence electrons. So what should be the group number? So this is a D block element because the last electrons enters into the D shell. So it is a D block element. For D block element, group number is equal to number of electrons in n-1 subshell and number of valence electrons. So number of valence electrons here is 5 and number of electrons in n-1 subshell. This is the electronic configuration of manganese. So in this case, we see that the last electrons enter into these shells, 4s2 and 3d5. So the period in this case would be 4 because that is the nth value of the last shell, right? But when we come to the group number is number of electrons in n-1 subshell plus number of electrons in the valence shell. So that means this 2 plus 5, that is total 7. So 7 would be the group number. Now this could be slightly a level above from what you are studying in your textbooks, but why I thought this is important is you should have an idea that how do we know an element belongs to which period and which group. However, the subshell level electronic configuration is something which you will learn in your 11th and 12th standard. So even if it is not very clear to you like how to write the configuration, that's okay. We have a video on chemistry for class 11th and 12th, so you can refer them. But for now, all you need to understand is this is the way we find out which period and which group an element will belong to. Hydrogen was placed on top of group 1 because of the similarity in the electronic configuration of hydrogen with all other alkali metals. So if you look at the electronic configuration of hydrogen, it has a valence electron 1, just like other alkali metals like lithium, sodium, potassium and so on. However, hydrogen also stood as an exception because the properties of hydrogen were not similar to that of the alkali metals, and that was primarily because of the small size of hydrogen. If you talk about the position of metals and non-metals on the periodic table, you would see that the number of metals are a lot more when compared to the number of non-metals. For example, from here up till here, these are all metals. So this side you have all metals. So you have fewer non-metals, and somewhere in between metals and non-metals you have a very few metalloids. I hope after watching this video you got a fair idea about the modern periodic table. If you have any questions so far, please feel free to put them in the comment section and we would be happy to answer. In the next video, we are going to learn something very interesting and important. So we are going to learn about the trends in the properties of these elements along the group and along the period in the modern periodic table. So stay tuned.